Hello, pre-calculus honors students. Here we are with the sine and cosine functions, and we're going to try and define the sine and cosine, know the values of the functions, and solve simple trig equations. First, a definition of the sine and the cosine. This is the formal definition, and we're going to have some easy ways to think about it in a minute, but for right now, if you've got a point xy on a circle, x squared plus y squared equals r squared, and theta is an angle in standard position, sine of theta is y over r, and cosine theta is equals x over r. Let's take a look at this on GeoGebra, on the definition of sine and cosine. Here we can grab this point, it's on this circle, x squared plus y squared equals r squared. I can change the size of the circle and so forth. But most, let's look at this, let's focus at this point 3, 4, or 4, 3. Should snap to it. Yeah, there's 4, 3. And notice that's not the sine and cosine, but when we divide it by r, this p over r is the point p divided by what I'm using for r now is 5, so I divide each of the coordinates of the point by 5, and now I've got both the sine and cosine of that angle. So the sine of theta is 0.8, and the cosine of theta is 0.6. In this case, theta is 36.8699 degrees. It's part of the 3, 4, 5. Notice if I change the size of the triangle, or change the size of the circle, xy is still a point on theta. I haven't changed the angle at all. And even though the point P is changing, P over R, the sine and cosine do not change. Okay. Now, that's the result we just did. So let's do some sample problems now. So, what do we want to do? Find the sine and cosine. If theta, the terminal rate of angle theta is in standard position, passes through negative 3, 2. So let's think of that point, negative 3, 2, there it is, and find the sine of theta. Well, we've got to get a few bits of information out of this. First of all, what's r? R is going to be the square root of x squared plus y squared. It tells us the distance away from the origin. Square root of negative 3 squared plus 2 squared. Now be careful there, make sure you put the negative 3 in parentheses because all of it has to be squared. And so you get the square root of 9 and 4, square root of 13. So square root of 13 is this distance, and that looks about right, somewhere between 3 and 4. That's the radius of our circle. And so the sine is y over r, so that's 2 over the square root of 13. And the cosine is x over r, so that's negative 3 over the square root of 13. Okay, let's try another example. If theta is in the fourth quadrant and sine of theta is negative 5/13, find the cosine of theta. Well, the sine of theta is negative 5/13, and we just said sine was y over r. Now, which one do you make negative, which one do you make positive? Well, you always make the x or the y negative. R is going to be positive because it represents the radius of our circle here. That's about the square root of 13 there. Or this is 13. I'm using a scale here of 2, 4, 6, and so forth. So we want the y to equal negative 5 and r to equal 13. So now you can go into x squared plus y squared equals r squared to figure out what x should be. X squared plus negative 5 squared equals 13 squared. I think you recognize this. 169. We get x squared equals 144. So we get x equals plus or minus 12. So we got 12 on the x. So 4, 8, 10, 12, and 5 in the y. And negative 5 in the y. Yeah, 12 is actually here. 2, 4, 6, 8, 10, 12, and negative 5, and that's about right here. So there's 12 and negative 5. But you can also see that negative 12, negative 5 would also satisfy having an r equal to 13 and having a y equal to negative 5. So this information alone is not enough to narrow it down. But when we realize it did say fourth quadrant, so we want to take this one. So that means we're going to go with x equals 12. So that means if the cosine is x over r, we get 12/13 for the cosine. Now, the unit circle. What happens if we shrink this whole thing down and have an r equal to 1? Now, when the point pxy is on the point on the unit circle, the formulas become easy. First, so the equation for the circle is just x squared plus y squared equals 1. And also then, the sine becomes y over 1, or just plain y. And the cosine is defined as x over r, or x over 1, or just plain x. So again, the sine is how high you are in the unit circle. The cosine, how far over. Cosine, how far over. There you go. Sine is how high, cosine how far over. So let's actually practice some of these. And first of all, let's look at the unit circle again. We could take our definition of the sine and cosine in terms of what we had here on our GeoGebra. And notice this is not the unit circle. This is on the unit circle. If we let r shrink down to 1, and now maybe make our scaling a little bigger here. Now we can see what's going on with the unit circle. And as we move this around the circle, now p over r, we don't really need to have that as a separate point anymore. And we just move this point around, this point xy in the unit circle, and now the sine is how high? So right at 0, focus on the y-coordinate of that point, and you get the sine is 0. The cosine is the x-coordinate, the cosine is 1. As we move this point up to 90 degrees, now the sine is how high? So the sine of 90 is 1, and the cosine of 90 is 0. And so these chords keep on telling us what's going on here. Here's 180 degrees. And at 180 degrees, the sine of 180 is the y-coordinate, that's 0. The cosine how far over is negative 1. So let's look at these examples. What's the sine of 90? Well, let's draw it in there. 90 degrees is straight up like this. It is the point 0, 1 on the unit circle. So I can just use the y-coordinate of that point, and we get 1. Sine of 90 is 1. How about the sine of 450? Well, think of the coterminal angle. It should equal the sine of 90. Because coterminal angles end up in the same spot and across the unit circle at the same spot. So 450 is the same thing. We just went around once and like that. So there's 450 degrees. And it's still the point 0, 1, so we still get 1 for the sine of 450. Sine of negative pi, this is going to be, remember, clockwise rotation. So we're going to rotate over here. So that's a rotation of negative pi. And you get to the point negative 1, 0. The sine is how high? So we get 0. Now, example 4, let's solve for sine of theta equals 1 for theta in degrees. So on the unit circle, y will equal 1. So we can think of the line y equals 1. And that only crosses the unit circle right there at the point 0, 1. So we'll get 90 degrees, but we'll get all angles coterminal with it. So 90 degrees and anything coterminal. So if the answer for this one is 90, add 360, 450, add another 360, we're at 810, We could also subtract and say, subtract 360, and we get negative 270, negative 630. We get a bunch that way. So you can express it all this way. You can say theta will equal 90 degrees plus 360 degrees n, where n equals any integer. And so we have an infinite solution set of problems for that simple trig equation, sine theta equals 1. Now, our next objective in this section, and this is actually section 7.4 now, there it is, evaluating and graphing sine and cosine functions. And let's use reference angles, calculators, or tables, and special angles to find the values of the sine and cosine and sketch the graphs of these functions. So, for an angle in standard position, the reference angle is the acute positive angle formed by the terminal side of theta and the closest part of the x-axis. What does this mean? Well, let me look at my little reference angle chart here, definition of reference angles. And what I've done here is I've taken a lot of the mirror image of this point x, y in the unit circle. So there's that angle down there. But I flipped it over the x-axis to get a point down here in the fourth quadrant, flipped it over the y-axis to get a point in the second quadrant, and rotated about the origin to get a point in the third quadrant. What do all these angles have in common? Well, first of all, the points have so much in common. You keep on just alternating the sign, but you have the same coordinates. And now what about the angles? Let's take a look at something like 60 degrees. And I'm going to do that on the scratch paper on a board. This is for an example of an angle of 60 degrees. If theta equals 60, then the reference angle is also equal to 60, because it refers to this alpha here, what's the closest part of to the x-axis. And it's always going to be positive. So it's not like the set the positive or negative referencing in terms of measuring off the positive x-axis. Now when we talk about a reference angle, it's this wedge, it's this angular wedge. So this one has the same angular wedge here of 60 degrees. So a reference angle of 60 degrees would refer to standard angles in positions of 120, because 120 is 60 away from 180. It would also refer to this third quadrant angle of 240, and also to this fourth quadrant angle of 300. All of these angles in standard position have the same reference angle, have the same wedge of 60 degrees between them and the closest part of the x-axis. The reason we're doing this is so that you can just use the sense of the sign of the coordinate and refer back to, that's why it's called a reference angle, the one you remembered in the first quadrant. So sine of 695 degrees in terms of a reference angle, first of all, we've got to locate sine of 695 degrees. Let's subtract off 360 so we get an idea where we're at here. That's 335 degrees. So we've actually gone a complete cycle around and then again some to 335 degrees. 335 degrees of rotation puts us in here. How far is that away from the closest part of the x-axis? Well, that would be 360. So to find the reference angle, we take 360 and subtract off 335, and we get to 25 degrees. So the reference angle is 25 degrees. 25 degrees is the answer. We want the sine of 695 in terms of the reference angle, so it becomes the sine of 25 degrees. But 25 degrees is in the first quadrant up here. And we take its sine, we'll get a positive number. If you take the sine at a fourth quadrant angle, it's going to be negative. So we have to put a little negative sign in front of that. So the sine of 695 degrees can be rewritten as the opposite of the sine of 25 degrees. Now, in these next examples, that was example 1. In example 2, I'm going to ask you to find trig values with your calculators. Okay? Make sure you know how to get to the right mode in your calculator. You can go to the mode menu. You can also look on the bottom of the calculator to see if the screen tells you what mode you're in. GRD is gradients. That's based on 100 gradients being perpendicular. Like when you see a 5% grade, that's 5 gradients. You're 5% of the way to vertical. Now, here's a little time-saving tip. I would keep your TI-9 in radian mode all the time. And if you come up with a problem in degrees, then you can just use the little degree symbol above the vertical bar key. That's one key left of the 7. And that should make it handy that way. Now, if you're looking for answers in degrees, then you might want to be in radian mode, instead of having to convert a radian answer, angular answer, and so forth. But when you're taking trig functions of various angles, that's a nice tip. Also, if you're thinking of AP Stats next year, you might want to try using the tables in the Navajo book on page 800. It's got some nice explanations on linear interpolation there, and that type of table reading skill is essential for AP Stats. So take some time to pause the video and try these on your calculator and see how you're doing with that. Make sure you know where to find the keys and all that. Did you pause? Okay, I'm going on. There are the answers: sine 122 degrees, 237, cosine 5, sine of negative 2. Now you notice that TI-89 sometimes gives you the simplified answer, especially when you're in auto mode, which is the mode I recommend. Just use the yellow diamond key to get the calculated answer before you hit enter. Diamond, enter, and then you should be fine. Now, do you remember special triangles from Algebra 2H and Geometry H? I hope so, because now we're going to move them on to the unit circle. And here we go. Here's our first special triangle. And it's basically with r equals 2, and I go, and this is a 30-degree angle in here. So if I make this a 30-degree angle, let's start with a big blue triangle out here right now. This blue triangle has a hypotenuse of 2, a height of 1, and a length of the square root of 3. See that 1.732 there? That's your 30, 60, 90 triangle. But now I'm going to put it into the unit circle. And when you do that, you shrink it down like this, making the R1 so that the height is 1/2 and the overness is square root of 3 over 2. And there you go. Whoa, stop it. Stop it right now. Okay. Here we go like that. There we go. Sorry about that, folks. Boom. Okay, so that's where we get 1/2 and square root of 3 over 2. For the sine of 30 is 1/2, and cosine of 30 is square root of 3 over 2. Now when we look at a 45-degree triangle, if I bring this straight down, in this case, I've made the hypotenuse 2, so the two legs are square root of 2 and square root of 2. See that 1.414? That's your 1 square root of 2 right triangle. If you multiply all three sides by the square root of 2, you get the square root of 2 right triangle. And this is at 45 degrees. 45 degrees. But if we take it now and bring it down to the unit circle size and make the r equal to 1, this becomes, divide this by 2, square root of 2 over 2, square root of 2 over 2. So the sine of 45 degrees becomes square root of 2 over 2, and the cosine of 45 degrees becomes square root of 2 over 2. Notice how I'm also going to let you take, I'm also going to just go ahead and let you write it as 1 over square root of 2. That's going to be handy when we do the cosecant and we take the reciprocal of that. Finally, this should be no surprise because we're looking at the same triangle that we did before, where this length is 1, this is the square root of 3, and the hypotenuse is 2. So when we trim it down to the unit circle size, bring it down like this, now you can see you get exactly 1/2 and square root of 3 over 2 for the y, and that radius of 1. And that's where we got that from. And so that's how you get the sine of 60 is square root of 3 over 2. The cosine of 60 is 1/2. Okay, now you can find a complete unit circle with coordinates at theflange.wikispaces.com on what's called the Handy Forms page. Handy Forms page used in many classes. And that also has charts of all the values of the trig functions that you have to memorize and so forth. Now this looks a little intimidating. How am I supposed to memorize all that? Well, if you can focus on things like the patterns that form here, like pi over 6 and 5 pi over 6. They're both over 6. They both have a reference angle of 30 degrees or pi over 6. And notice the coordinates are very similar, square root of 3 over 2 and negative square root of 3 over 2 comma 1/2. Okay? And so if I want to do something like the sine of 120 degrees, here's 120 degrees. The sine is how high? So you get square root of 3 over 2. Notice that height, the y coordinate, looks like about square root of 3 over 2. Start getting these ideas down that 1/2 is 0.5. Square root of 2 over 2, or 1 over square root of 2, is about 0.707. And square root of 3 over 2 is about 0.866. And that comes in handy then when you do things like, what's the cosine of 135 degrees. Here's 135 degrees. The cosine is how far over. Now, if you didn't have the chart, and if you just brought this x-coordinate down to see how far over it was, if you had your choice of these three numbers, you wouldn't say half. And you might be torn between these two because they're kind of close, but you got to remember that the 135, the ones with 45 degree angles, use that square root of 2 over 2 one, so that's the square root of 2 over 2. Let's try some more. Let's look at the sine of 210 degrees. Here's 210 degrees. The sine is how high? Notice how the y-coordinate there is negative half. Negative half. How about the cosine of 315 degrees? 315 puts you into the fourth quadrant here. The cosine is how far over? Yeah, that's square root of 2 over 2. It's positive, right? Whenever you have the ones like square root of 315, 225, there you go, 135, the ones that end in 5, the special angles that end in 5 like that. The ones that have a reference angle of 45 degrees will have plus or minus the square root of 2 over 2 for their answer. You decide which it is by looking at what quadrant you're in. In this case, we're in quadrant 4. Okay, I'll leave that one blank in case you want to do some more problems. Now, you might say, that's all well and good, Mr. Flash, but what do I do without a unit circle in front of me? Draw. Let me show you some drawing techniques. Except, I have somehow, yeah, there we go. Good, okay. Draw. And remember, the sine is how high, and the cosine is far over on the unit circle. So if someone were to ask me, just on a blank sheet of paper here, what is the sine of 210 degrees? I just draw a quick circle. 210, I locate that. That's somewhere between 180 and 270. It's 30 degrees beyond, so it's this shallow one like this. There's 210. Sine is how high? The sine is how high on the unit circle. So I come over here to the height, and I go, wow, that looks like negative half. And I'd be right. Boom. That's how easy it can be. It's not a matter of memorization of a huge amount of data. It's memorization a little bit and applying concepts of reflection and symmetry to come up with the other answers. Now, for the graphs of sine and cosine, to graph the sine function, imagine a particle on a unit circle that starts at 1, 0 and rotates clockwise around the origin. Every position x, y on the particle corresponds to an angle, theta, where sine of theta equals y by definition. As the particle rotates through the 4 quadrants, we get the 4 pieces of the sine graph. Let's see this in action. Generating sine curves. Here we go. So what I've done here is I've gotten this on the unit circle again. And here's a point on the unit circle. And there's one thing you have to realize here, that the input for the sine wave is an angle. And in this case, I can't just use this angle that I have down here, measures 132 degrees. I have to use the input as the x, because my scaling here is not in degrees, it's in numbers. So I actually take the arc length, and that's my input, the actual arc length. So I measured the arc along here, and didn't measure it like you did in geometry in terms of degrees. That would be the same as the central angle. I'm measuring it the actual length, and that actually gives me the unit in radians. Notice down here, when I'm comparing these two, d, which is the arc length, and the angle here, that's basically just what is in radians. Remember, 60 degrees, let's get this around 60, is about a little more than a radian in 1 radian. It's about 57.3 degrees. Okay, so that's what I'm doing. For the input for the sine, I have to take the arc length along this from from 1, 0 to the point on the unit circle. And the output then is going to be the actual height of the sine wave. The height, the sine is how high, right? So I take the y-coordinate off this point. And that's what I did here. And I'll re-show these again. Intersected those two lines basically. See that? Where the input is the angle measured in radians, so it's going to be along the x-axis, and the output is the y-coordinate. So let's hide those again. Focus on this point now. Now what I want to do is take this point the point on the curve. And this is where I want to go to Object Properties and basically show the trace of this point. So now when I start moving around this point, you can see I'm generating the points on the sine wave. Notice how as I keep going around more and more angles, it's going to keep repeating, but it is going to go further down that way. And from this we can come up with a nice sketch of the sine curve. Okay? Yeah, notice here too at the start that you're not pointing for this peak right here. You're pointing about 50% higher than the peak. And then it starts bending right away. Keep that in mind as we start to draw these. So that's the sine and cosine graph. There's the results. Now let's practice drawing some sine curves. The sine basically goes omamo. 0, max, 0, min, 0. And so what I see a lot of kids doing is they don't put a lot of time into it. They got to connect the dots. Oh, Neller. No, it does not connect the dots. I see some other kids trying this. They go, oh, okay, yeah, I know not to connect the dots, but I see a semicircle here and I see a semicircle there. No, the sine wave is not a bunch of semicircles. Look at this. It doesn't get vertical there. As I was saying, right at the start here and here, it's got these slopes that are pointed about 50% higher than the maximum. Then I see some kids doing this. They go, oh, yeah, I got to go through the dots. That's a duck. Yeah, flack. And that isn't big no. No, the sine wave is never linear. Okay? And look at this. Somebody passed the flunked the vertical line test. So that is unacceptable. So how do you do it? How do you get past my stringent test on a decent looking sine wave? Well, here goes. You start here at the origin, you start here at the 0, and don't aim for this maximum right away. Aim for about 50% higher. Keep your eyes on that point right there. So if you do that, and now just draw a nice smooth curve through here, you're going to be much better off. Now notice I missed a few dots. If I just go over it a few times, it's looking better and better. Oh, triple. Okay, there I left some for you to practice on. The cosine goes mamam. So, no, we're not just going to connect the dots. No. Okay? What we're going to do is think of what happens here at the peak. It's horizontal. So you actually aim for the other peak, and just dip. That's nice. I didn't like it in there so much. There you go. That's a nice looking sine wave. Cosine curve, cosine. Kind of looks like Georgia O'Keeffe's skulls. Cow skulls. There you go. There's the cosine. Okay, have some practice with those. And flange. Oh,